Hello friends, today we are going to talk about the another topic in the thermodynamics, that is temperature entropy diagram. As we are aware that we must have studied earlier as well, right, about the PV diagram, right, that is pressure volume diagram. Similarly, we can define the thermodynamic state of the system by using the temperature and entropy diagram, right. As we know that the state of the thermodynamic substance can be defined by the two independent variables, right. So two independent variables, which are they? Okay, or two independent variables, out of which how much we can see? Either we can have the pressure, volume and temperature, right. So this is the equation we can use for the equation of the state, right, out of which we can define the system by choosing the only two independent variables, and the third variables will be automatically fixed by the equation, that is a PV is equal to nRT. N is nothing but the number of moles of that particular substance, right. Similarly, we can have the one more additional independent variable, that is nothing but the entropy as well, right. It is also the state parameter, so we can define the one more parameter of that particular system, that is entropy, right. So out of these four variables we can choose any two variables and we can define the state of the thermodynamic system completely, right. So normally we can have that state of that thermodynamic system can be defined by this equation of the state, right, and it is well known as the PV diagram. Similarly, we can have the another kind of the diagram to represent the state of the thermodynamic system, which is known as the temperature and entropy diagram, or else it is known as the T and S diagram, right. So T is on the vertical axis and S is on the horizontal axis. As we can see on this diagram, that is state A, okay, or the point A represents the state with the entropy S1 and temperature T1, and similarly the another state of the system is the state or point B, which is represented by the temperature T2 and the corresponding entropy is S2, okay. So now the curve which is passing through these 2 points, right, so it is by just following this curve. So curve AB is representing continuously changing the state from its initial state A to the final state B, or else vice versa. So it is just can move the system or change its state system between the A and B continuously, right. So now when we are changes when we are considering the changes happening within the system, when it is undergoing from the A to B, then the change of the entropy or change in the entropy of the system because of an infinitesimal change of the state from the A to B, okay. So smaller changes we are just considering from the when the system is going from this to this point, then that is given by is nothing but the ds is equal, so small infinitesimal change in the entropy is given by dq by t. Dq is nothing but the change in its heat, okay, or amount of the heat gain or loss by the system, okay, at a particular temperature T, right. So we can have the define the dq, okay, dq is equal to T ds, T ds. So T is the temperature at that particular the changes are happening, and ds is the width of the entropy or change, okay, or width of this entropy change. So this dq represents nothing but the area of the this small strip, okay, this small strip a b b dash a dash, right. So the area of this strip can be understood by the amount of the heat change within the system. So now this area gives the amount of the heat absorbed by the system in going from the state A to B. Hence the total heat absorbed by the system, okay, total heat absorbed by the system when going from the state A to state B is given by the integration, that is amount of the heat is or total amount of the heat gained or is given by the integration dq from going from the A to B, so TdS. So this is nothing but the whole area under this AB curve, okay, or area under this AB curve, okay. So what we can say, area of the AB B dash A dash. So this much whole area is considered as amount of the heat gained or the absorbed by the system, okay, when the changes are happening within the system when going from the state A to the state B. So the total amount of the heat absorbed in the system when it is going from this A to B is given by this above curve, that is TS curve and S axis, okay. So the area under the curve TS, okay. Now let us consider the another example or example of the Carnot cycle, right. So is a well known example in the thermodynamics, that is the Carnot cycle, as we have seen in the previous few lectures as well, right. So as we know that the Carnot cycle has 4 operations, okay. So the 4 operations can be seen over here, right. So the 4 operations can be seen over within this diagram, okay. So the system is going from the C1 to C2, C2 to C3, C3 to C4 and C4 to again coming back to its original point, that is our initial state as the C1. So what is happening within this 4 operation, let us try to understand, and what type of the changes are happening within this system is represented in this diagram, and let's try to understand that how these changes are considered, okay. Now when the changes are happening, or when the system is going from the C1 to C2, okay, so this changes happening, okay, you can see on this diagram as, okay, there is no change in the temperature, right. So temperature remains constant throughout, and whatever the changes are happening in the its entropy. So when the system is going from the C1 to C2, okay, when the system is going from the C1 to C2, that is called as the isothermal expansion, okay. Isothermal expansion, obviously it is at the constant temperature, okay, at a constant temperature it is happening, and the temperature is T1, okay. So the amount of the heat Q1 is absorbed, okay, amount of the heat absorbed by the working substance, and the is Q1, and because of the absorption of the heat, okay, heat is absorbed. So what we can have, the amount of the changes happening within the entropy is from the S1 to S2, okay. So the amount of the changes happening in the entropy is S1 to S2, so that is represented by S2 minus S1, S2 minus S1. So the total heat is nothing but the area under that whatever the curve which we are considering over here. So the area under this curve is we are trying to understand. So C1 into C2, C1 C2 into C1A, C1A is the what we can say the area under this curve. So the how much is the C1 C2? C1 C2 is nothing but the S2 minus S1, and what is C1A? C1A is, you can see over here, C1A is nothing but the at the temperature T1, okay. C1A is nothing but the temperature T1. So the Q1 is equal to S2 minus S1 into T1. Now the another changes, the system is trying to make the change from the C2 to C3, okay. Now this changes are happening, that the process is adiabatic one, adiabatic expansion is happening, okay, adiabatic expansion. Now the adiabatic expansion, no exchange of the heat, so heat remains the constant, so obviously there will not be change in its entropy. So what is happening, entropy remains constant, that is remains at the S2. So the adiabatic expansion is happening, and the temperature is decreases from the T1 to T2, okay. So this is a decrease in the its temperature, and obviously what we can say, the entropy remains a constant, that is at the S2, okay. Now the another changes are happening from the C3 to C4. Now we can see the entropy is again changing from the S2 to S1 at the constant temperature. So these changes are happening at again the isothermal compression. Okay, isothermally happening, but what is it? This is the compression. Earlier it was a expansion. Now here it is a isothermal compression at the temperature T2, because our system has come to the temperature T2. Okay, so the isothermal compression is happening when the system is going from the C3 to C4. So the amount of the heat given out, okay, given out, because when it is compressing, obviously it has to lose its heat energy. So the amount of the heat energy given out by the system, and there is Q2. So the Q2 is equal to area under the rectangle C4 C3 BA. Okay, C4 C3 B into A. So area under this is nothing but the amount of the heat given out. So this is nothing but this rectangle C4 C3 into C4 into A. So this is something like this is the rectangle. So this length into this length. So whatever is S2 minus S1 into T1. So amount of the entropy change is S2 minus S1. So now again, when the system goes from the C4 to C1 to coming back to its original position or the initial state, then obviously this process is happening as happening or is called as the adiabatic compression. So this happening as the adiabatic compression. So at that what we can say, there is a no change in its entropy is happening, no change in its entropy is happening. So and the temperature, because of its what we can say is the isothermal adiabatic compression, so temperature is changed from the T2 to T1. Okay, temperature is changed from the T2 to T1, or the temperature gets increased here. Okay, so temperature increases from the T2 to T1 because of its adiabatic compression. So we can have the how much amount of the heat exchange, that is Q2 by Q1. Q2 by Q1 ratio is considered as S2 minus S1 up into T2 upon S2 minus S1 up into T1. So this will get cancelled out, and what is the remaining? T2 minus T2 divided by T1. T2 divided by T1. So as we know that the efficiency of the Carnot cycle is eta is equal to 1 minus Q2 by Q1. 1 minus Q2 by Q1. Similarly, you can define the efficiency of the Carnot cycle in terms of its temperature, that is 1 minus T2 by T1. So this is all about the TS diagram.